So it's the last talk, and I thought nobody would mind if it was a short talk and it had just a few simple points that I wanted to communicate. And there's a great advantage there because I don't have any detailed points that I could communicate about the evolution of psychological categories. I think I might know a little bit about categories. I don't think I know anything about evolution. I certainly don't know anything about language or game theory. So I really have fewer than 20 slides, which has to be an absolute record for me in any form of presentation, let alone an hour one. This will not go for an hour. First thing I'd like to do is a disclaimer, especially for the people who are sort of core cognitive science people in the room. There are at least two ways, but two obvious ways that if you're interested in Bayesian statistics or hierarchical Bayesian statistics, you could apply them to a cognitive modelling problem like understanding the nature of psychological categories. The obvious one, perhaps, is that you could use Bayes as a statistician would, as a way of analysing your models and data and relating the two to each other. The second way you could use it is as a theoretician would. So you could use Bayes as a working hypothesis for how the mind would solve an inference problem like inducing the representation of a category. Now these are clearly related in some ways, but they are very different things in the way they play out in practice. And those of you who come from cognitive science will know why I'm making this distinction. There's some outstanding work in the last 10 years or so, some by people in this room, like Tom Griffiths and Josh Tenenbaum would be another name I would associate heavily with it, who have done the second and perhaps the less obvious application. They've used Bayes as a working hypothesis for how the mind works to develop various rational accounts of aspects of human cognitive behaviour. And so the reason I mention it is if I had a nickel for every time a reviewer has got upset where I've said a Bayesian account of, because they've assumed that I'm going to assume this is the way the mind works, where really all I want to do is use it as a statistician does to relate my models and data in a principled and coherent way. Well, I guess a nickel, you know, I'd have $1.25 or something, but it's happened enough that I wanted to mention it up front. So this talk is going to take the first approach. All of the Bayesian stuff you see here is as a principled and coherent way of relating models to data, and I'm going to try and flesh out how I think that's helpful in taking some standard cognitive process models and some standard models of representation and understanding the nature of categories a little better. So here are the sort of core elements that are going to go together to make the talk. There are two specific debates in the cognitive modelling literature that I want to play into. One of them involves a debate between exemplar and prototype representations, and this is basically a debate about the level of abstraction involved in representing a category. At one extreme you have the notion of exemplars where every single instance of a category is represented somehow. At the other extreme you have the notion of a prototype, which is just some central or summary representation that stands for the category. The second debate I want to talk about is one that involves the emphasis on similarity in forming category representations. So to what extent rules that might combine quite different stimuli because there's the language or the verbal ability to combine different things are used as the basis for a coherent category representation, and to what extent similarity is the driving force. Now, I think, and I'm sure you all think, both of these debates are a bit silly because there's clearly no unitary answer to either of these debates, and there will be different circumstances where different levels of abstraction have different degrees of importance, and context will be important, and so on. And exactly the same for similarities and rules, the extent to which you encourage one over the other. And in fact, Greg Ashby's talk on Friday was very much looking at distinctions. The information integration you could think of as being the similarity type one, and the verbal rule you could think of as being the rule type one. Having said that, if you read some passages in the literature, and many of you will know this literature better than me, it's amazing how much people behave as if they really do believe there is a dichotomous debate between exemplars and prototypes. And I assume this is just sort of social and personal acrimony or something like that. But there are certainly passages in the literature where they look like there is a debate to be addressed here. So I'm just going to have those two debates as things that people might want to know about category representation, sort of goal for doing your modelling and collecting your data to address these debates. And I'm going to do that by looking at two existing models, and I also don't believe in either of these models at all. So in fact, all of the background material on this slide are things that I have absolutely no commitment to. These models both fall in that classic class where all models should, where they're clearly wrong, and they're clearly wrong in all sorts of important ways, but they both might be useful for some current purpose. So one is the generalized context model. This is a similarity-based account of how people might associate stimuli with categories and pay selective attention to different dimensions of those stimuli to learn about how stimuli come to be associated with categories. So if you like, it's a behavioral model for how people might produce categorization behavior in some task, how they might produce the behavior we observe experimentally. And then the varying abstraction model with my collaborator Wolf is an account of different types of possible category representations, and in particular it's one that tries to interpolate between the exemplars and the prototypes as two extremes of a spectrum, and that's going to be useful for what I do want to achieve. And so here are really the goals, and I can't believe I'm going to say this, but the Bayesian bit isn't the really important bit here. The hierarchical bit is the important. You could probably do this as a frequentist or something if you had half your brain removed and you wanted to work a whole lot harder. You could probably do this just with hierarchical modelling, but Bayesian modelling has all sorts of advantages like being much easier. So it's going to be hierarchical Bayesian. And so here's what I really want to show. I want to show how thinking about these psychological processes hierarchically encourages you to theorize at different levels of abstraction, and that this is a really useful thing. You don't just sort of have parameters at one level of abstraction, you can think about them themselves being generated by some more abstract psychological process to give a more complete account, and this will play into ideas like evolution. I'm going to show, not covert, it's not hidden, it's meant to be convert, how using these sorts of approaches in a model theoretic sense, in a sense of just doing your modelling, convert what's typically a hard and limited model selection problem into a much easier and much more informative problem of estimating parameters as a deeper level of abstraction. You have this notion that your models come from somewhere, you can now think about, rather than just choosing between them in a 0-1 sort of way, of estimating the proportion in which they're generated by these more abstract processes. I'll try and make this concrete with an example in a minute. I'm going to try and show how thinking about things hierarchically can make things commensurate across multiple tasks and experiments, because you now are thinking at enough of a level of abstraction that information from one can be absorbed with information from another, so you can model multiple things simultaneously and get the power that that provides. And I'm going to talk about how thinking hierarchically is one way you could develop theoretically satisfying priors for the models that you might want to develop. It's often a sort of criticism, in inverted commas, where people complain they didn't do Bayesian analysis because it was very hard to come up for priors in models. Maybe sometimes that's true, but I'm going to try and show an example here where you can get very sensible priors that are very much not the ones you would assume if you just made them uniform or something like that. Okay. So here's what the Wolf's varying abstraction model does. It assumes that different types of category representations can be formed by merging different subsets of the basic stimuli. So I'm going to use this formalism quite a bit. Each of these dots you can imagine is one of 4 stimuli that make up a category. So these are just the 4 stimuli in a category, and they vary on 2 spatial dimensions. So these are just low-dimensional geometric stimuli. So one indexes the height of something and one indexes the width, or something like that for the 2 axes. And so the classic exemplar representation would be this one of the category, where all of the stimuli are just represented in the category, and the prototype representation would be right down here, where they've all been merged into some sort of central tendency capturing the prototype. And Wolf's very simple idea was you can naturally interpolate between these two by allowing any subset of the stimuli to be merged. So in panel B here, 2 of the original stimuli have been merged into a sort of sub-prototype, and the other 2 have been maintained in their exemplar form. And this gives you another representation of the category. And by following through and looking at all the possible subset merging, and this is well known to mathematicians as a Bell sequence with a Bell number of things to merge, you end up with a whole lot of possible category representations. Yeah.
Say something about the green box?
The green box merges some of them. That was all I wanted to say about the green box at the moment. I'm going to come back to boxes with different colours to make some more detailed points about these. Yeah. So the point is the van can represent merging none, some, or all. That's all I wanted to say. And then even less detail on this because it's even less important, but just to give the formal details that with a category representation you can map it into observed choice behaviour in a category learning task, sort of task where you present people with a stimulus and they respond with one of two categories and you give them some feedback as to whether they were right or wrong, and over time you learn to do better. And so this is super familiar to many of you, but the basic idea is that first of all you calculate the distances between all the representing points. Secondly, you calculate some notion of similarity as a decaying function of the distance in these psychological spaces, and then you have associations of each of the stimuli to each of the categories, and you have a sort of weighted sum that gives you choice responding behaviour. And there are a couple of parameters floating around in there. So here's what Wolf originally did, and in fact Wolf came, well this was back when I was in Adelaide, so it's a number of years ago now, but Wolf came out for a 3 or 4 month visit and he just started working on his PhD thesis, and he had this VAM class of representations and he was doing inference, and basically he was doing inference something like this. He was observing some categorization behavior, he had some set of possible representations, those ones I showed you in all of the panels, and he wanted to infer which one people were using. And he'd done a bit of this and he was doing sort of least squares fitting and maximum likelihood fitting and stuff, and we immediately sat him down and said, if you want to stay in this lab, you're going to have to do full Bayesian model selection, otherwise we're not going to let you stay. And so it literally worked out that his 4 months visiting in Adelaide, he calculated 3 integrals, because he had to go back and learn a whole lot of important sampling and other techniques for evaluating marginal densities that you needed in these model comparisons, and so his entire work over the 4 months was to produce these 3 numbers. And so this is, I think, one of the problems with the approach he was taking, and I think there are a couple of others, and they're related. So what Wolf was doing when he was trying to infer which one of those panels was the correct representation given the data that were available, was he was implicitly assuming that all of them were a priori equally likely, that all of those representations were equally good ones. The second thing was, as I just said, it involves significant computation to go through and work out which one of these is preferred if you want to balance up fit and complexity in a principled and coherent way. Third one is that he had no notion of the obvious relationships between each of the representations, like some of them abstract more than others in any of his formal modelling. And the fourth one was he had no account of where these representations came from. And let me just illustrate all of that with this additional panel. So this is the one I was hinting at, Kimberly. So first point was he thinks all of these are equally likely in the way he was going about his modelling. But I would say one's in blue, like A, and one's in green, and one's in red, look far a priori like more likely representations of a category structure than, for example, something like D, which seems to involve a very strange merge of very dissimilar stimuli.
By a priori, it's not less than positions, it's less than.
Yeah, given that those points have spatial meaning and capture similarity relationships between the stimuli. Yeah. That's right. And so a uniform prior seems like an inappropriate prior to have if you're going to go about doing this inference. It also has the problem that if, for example, he made an inference where I can't quite tell whether it's A or B, but I'm pretty sure it's one of those two people are using, and from finite and sparse data you always make uncertain inferences. If he said it's either A or B, but I'm not sure exactly which, that still seems like a satisfying conclusion, because we could still say, well, whatever it is, it's a pretty near exemplar sort of representation, and people aren't doing much abstraction when they go about doing this. Whereas on the other hand, if he'd said, I can't really tell which one it is, but it's either A or O, this is a very unsatisfying conclusion because it doesn't answer any of the basic questions. But notice that when he's doing that, he's just interpreting something he can see about the structure of relationships. None of that is formally captured in the model anywhere. To the model, these are all just nominal different things, and the conclusion is actually identical. There are 2 of them that are possible, there are 2 of them that are possible. Any of that active interpretation about abstraction isn't captured by the model, but it's exactly what you want the model to capture. Okay.
Yeah. Is it true that if for L, if you connected the 2 black dots with one in the middle, you would get O?
Yeah. And so the hierarchical extension is going to try and address all of these problems. And it's exactly what Wolf was originally doing with one additional level. And this is going to be a level that has a theory about how it is that those VAM class of representations could come to be generated. I'm not going to say that it's a great theory, but it's just one working theory. And it's going to be driven by two parameters. One's going to directly control the degree of abstraction in the resulting representation, so how many of these merges take place. And the second one, gamma, is going to control the emphasis on similarity, so how likely it is that nearby stimuli are ones that are merged if the merge takes place. And you can see that under this sort of conception, theta and gamma immediately correspond to the sorts of questions you are interested in. So theta indexes the exemplar to prototype distinction about how much abstraction is going on. So inferences about theta, I should say theta, shouldn't I? Yeah. Inferences about theta, Tom's smiling at me. Inferences about theta immediately tell you about exactly one of the questions you wanted to know about the debate. Inferences about gamma tell you about how great a role similarity is playing, and so tell you something about the similarity versus rules debate that I wanted to play into. So the parameters are set up to have the semantics for the questions you actually wanted to answer.
Maybe you're going to get to this, but I guess it's not entirely clear to me. It's clear to me what role theta is playing, but gamma, how exactly is that?
I'm going to say how exactly
How that hashes out the similarity versus rules.
Yes, I'll say that probably on the next slide, I think. So let me just make sure that the overview is clear. The idea is we've added an additional hierarchical level to this account so that rather than the VAM representations just arriving with some uniform prior and no structured relationship between them, they're now being generated by a process that has some semantics and has some interpretable parameters. And this is going to tie them all together, allow them to be related to one another in formal ways, and allow inferences about them to have meaning at a greater level of abstraction at this similarity versus rules and prototype versus exemplar level of debate. In fact, yeah, here it is. So here's how the merge process works, and I'm sure you could come up with a more psychologically sophisticated one if you wanted to, but I'm trying to make a general point here. So you start with the exemplar representation, you merge with some probability theta, and if that theta condition isn't met, then you stop, and that's the representation you end up with. So you could end up with just the exemplar representation. On the first step, you decide not to merge, you stay there, you end up with the exemplar representation. If you do merge, you have a look at the similarities between all of the points that are currently in your representation, and you choose a merge probability according to this thing, which could be called an exponentiated loose choice function, if you like. This is really just chosen for convenience. They're very standard in the literature. It's a neat, easy way to do it. And the important point is that that gamma parameter controls the emphasis on similarity. So as gamma gets very large, only the most similar pair will have any probability of being merged. As gamma gets very...
It's very hard to see. It's the exponent.
It's the, yeah, exponent. So as gamma gets large, this number is only going to be big for the pair that is the most similar pair. It's going to act as a gain, basically, to do that. As gamma goes towards 0, it will just be equally likely that any pair will be merged, and when gamma's about 1, it's not exactly probability matching, but it's something like probability matching. And you do this repeatedly. And so if theta is high, you will be doing lots of these merges. If theta is low, you'll be doing few. And in fact, I have some concrete examples here. So high theta values encourage lots of merging and result in more abstracted or prototype representations. High gamma values emphasize similarity in merging. So here's that whole class of representations that we've been working with the whole time, but just arranged in a line now, starting with the exemplar on the left and the prototype on the right. And so if theta is a very high number, lots of merging, we're going to very likely generate the prototype representation through this merge process. If theta is very low, we're going to very likely generate the exemplar representation. Theta for the next 3 panels is just going to take some intermediate value so that it's possible to have all sorts of levels of merging. If gamma is right down at the 0 level, then all of these intermediate ones are equally likely, at least within the counts of the same number of merges. So these are all the ones with 1 merge, and these are all the ones with 2 merges. So similarity is playing no role. But as gamma becomes progressively higher, only a couple of these representations, one for the 2 merge case and one for the 1 merge case, become likely, and they're the ones that have the similar stimuli.
So rule-based is sort of hyper-similarity.
The only way you're going to get a rule-based one, if those rules encourage things that are dissimilar stimuli, is by driving this parameter right down. And so inferring a low value of this is diagnostic that similarity-based isn't what's happening here. Yeah. And so here's the first major point. Well, yeah. I guess the first major point I wanted to make here is this now ties together the representations in a formal way. So the reason these two guys look similar is that they both generated similarly under high values of gamma, for example. So this now gives a way of formally relating what we could already see about the level of abstraction and the emphasis on similarity in the representations, but they now have a parameterization that captures those semantics. Second one is, because this is all Bayesian, you need priors on the thetas and gammas right at the top level of your hierarchy. We played around with all sorts of reasonable things, and it makes no difference qualitatively and very little quantitatively here. But for any choice of priors, you instantly, immediately get some prior prediction about how likely each of those category representations is. And so you can view this as an inductive bias or a prior representation on the categories. Before you've observed any data, some category representations are more likely than others. And here's what it looks like. We actually expect to see an exemplar or a prototype representation, and if it's not going to be that, it's going to be one of these very plausible looking ones, but very unlikely to be one of these strange ones. So if you like, this is a theoretically based, in the sense that we can say what theory it came from. This is a theoretically based prior, where Wolf previously was just assuming a uniform prior across things. And this will, of course, matter more with sparser data. So if you have fewer data and you're trying to infer what category people are using, this will have a greater impact. If people are really using this, it's no problem. You'll see it after a while. It's just you'll need more evidence to see this, because it's not what you expect on the basis of believing that there are degrees of abstraction and emphasis of similarity in category data. So I think all of those previous shortcomings I mentioned have been addressed one way or another. So I said that he implicitly assumed a uniform prior. We've now got some sensible priors, and we can see where they came from. We're now no longer choosing discretely between two models. We're now just trying to estimate levels of theta and gamma that characterize the sorts of representations that are being used. We now have a formal notion of the relationship between these two, because similar theta gamma pairs will index similar representations, the right semantics, and we've got an account of where the representations came from. Okay, so what did we do with this? Well, I didn't do this. Wolf took every data set he could possibly find that was sort of directly applicable and relevant. So here are 30 data sets, all with Nosovsky's name on them, but those of you who know that this is almost unavoidable in this subset of the field. They do span all sorts of interesting dimensions. So there are colors and circles and tones and all low-dimensional perceptual type stimuli, I would say, but quite variable, modality and whether they're integral or separable stimuli for people who are interested in that sort of distinction and so on. Some of them are single subject data, in fact many of them are, which is nice. Some of them are group data. Some of them involve issues of whether people were allowed to just classify freely or whether they were trained on rules, so we can have a look at that debate. Some of them, and this almost gets to the topic of the conference, involve beginning, middle, and end blocks, so we can have a look at how the category representation evolved over a series of time. So what I wanted to do now is just go through and cherry pick a set of results that relate to the debates and try and show these nice features of the model in action on those. So each of the numbers you see above the panels here just relates to one of those data sets. It's just numbered because I cut and pasted it from the paper, and it was important to have the cross-referencing in the paper. So you can see for some of the data sets, we infer that people are using very exemplar-like representations, and for other data sets, we're inferring that people are using very prototype-like representations. And this is sort of as you would expect and hope. There's no one answer, but different sorts of category structures and different sorts of tasks encourage different levels of abstraction. And some are intermediate. And you can see all of this in the posterior distribution of this theta parameter, when you go and do the inference. So when you get a high level of abstraction, you get a theta value that's very close to, or has lots of density for 0. When you get the heavy prototypes, you get a probability of merging continually that's near 1. And so the theta distribution that you get tells you about the level of abstraction in a very direct way. I should say, I've only picked out 3 of the posterior distributions there for sort of legibility, and they're the ones that are highlighted by the,
So the
3 boxes.
dotedness or non-dotedness of the outline corresponds to the dotedness
Yeah,
or non-dotedness
these match.
of the, yeah.
Wasn't that diligent of me? Yeah, yeah. Sometimes we get an answer which is basically the model has no clear answer, so these are now not different data sets. This is for one data set, the model saying, I think there's a 36% probability it was this, a 20 it was that, a 12 it was that, and a 10. So I'm really uncertain about this now. One possibility is people are really using a mixture of all of these. Another possibility is the models are so badly misspecified that it does model averaging, which is what models tend to do when they're badly misspecified. But at least this is all clear. I guess this is one nice bit about the Bayesian inference. It represents this uncertainty because it's able to very directly, and you know that there aren't strong conclusions about exactly which representation, and you can see an awful lot of uncertainty floating around in the posterior. I don't know whether these, Tom, can these technically be called multimodal or just non-monotonic? You know, I guess you can argue they've got 2 modes. But in any case, the theta tells exactly the same story, where it's really unclear what the level of abstraction is here.
When you say misspecified, does that mean anything other than the experiment doesn't provide evidence that pulls things apart? Or does it
It means the models are so bad that they can't generate data. So the assumption would be, in the modeling that's presented, that there is exactly 1 theta and 1 gamma. And if that's wrong, if the models are badly misspecified, the way Bayes will try and get out of that is to average across lots of thetas and gammas, all of which, when blended, looks something like the data. And so a very standard heuristic sort of diagnostic when you're doing Bayesian modeling is, you know, you've got a bad model when all your posteriors just go flat, and it's just trying to find little bits and pieces of what the data look like and blend them all together and hope that that roughly looks right. And you know you've got a great model when your posteriors go really peaked really quickly because it can find exactly 1 point in there that looks like the data.
But it's pretty clear, right, that if the exemplars are all really clustered, then the model that says you're just using the exemplars and the model that says you're using just the prototype are not going to make any, they're not going to be any different in terms of their prediction.
Right.
So it could be a problem with the experiment. Not so much
That's also possible, although all of those experiments were in the middle of an exemplar prototype debate, and I suspect they were they're probably fairly well controlled so that these things weren't making identical predictions, because I'm sure that was part of the motivation. And I suspect they were probably biased towards supporting exemplar type representations,
Right.
because that was probably the bias too.
Sure.
But you're right. So diagnosticity of the model in the way that it relates to the data could be blamed on the model or blamed on the data or blamed on the combination of the two. And I guess my answer was more geared towards the modeling side of things, but it could also be the data. Yeah. Here's the time course of representation. So these relate to the same data, the same task, but looking at data from the beginning, middle, and end of the learning trials, and the beginning, middle, and end of a different task. So you can see in one of the tasks, you move from something that has some level of abstraction to a much more exemplar-like representation over the course of learning. And a similar-ish thing happens here. It's not quite so strong, but there's still some notion of initial mergings going on. And you can see this again in the theta parameter. So at the beginning, there's some level of abstraction, but at the end, there's much higher density towards no abstraction. The same over here. And I think one of the really important points I'd like to make here is we didn't do this, but we could, and we probably should. There is no reason now that we have a hierarchical model, even though these are different experiments with potentially different stimuli or different category structures, there's no reason why we couldn't model both of these simultaneously to become even more certain about this. At this level, you could well have different stimuli and different category structures, and there would be no way commensurately of combining your results across the two experiments. At this level, the parameters are quite commensurable. Theta means what it always means, and it means the same for every task in every experiment. And so you could simultaneously model all of these experiments at this level and draw much stronger and more definite conclusions. Does that make sense? You look puzzled, Jay.
I'm thinking I'll ask a question later if I figure out whether my puzzlement is just kind of a problem.
Okay. I sort of think this is a nice point because this doesn't happen nearly often enough in psychology. Too often there is one phenomenon for which we have one task and then we have one model for that task and then we'll move on to the next one. But if you really believe your parameters are about some fundamental latent psychological property, this ought to be manifest in multiple tasks, multiple times. And hierarchical models are an ideal way of capturing that in a formal sense. So if your modeling becomes abstract enough, then this latent psychological variable can, through different process models, play into different tasks, but you can make inferences about it simultaneously from all the evidence you have across all of the tasks that are relevant.
Can I ask a
Yeah.
question? Maybe orthogonal to that point. When I look at these graphs, I see that there's a difference between your posterior for the value of parameter at the beginning of the experiment and the value of parameter at the end. And so I'm trying to figure out whether this means that you conclude from this that the subjects are somehow changing their strategy over the course of the experiment, or whether you just don't have a model of the learning process in which there's a stationary underlying sort of representation that plays out differently as more data is collected.
Right. So I would view it at this stage as the model is sort of a measurement tool saying it looks like abstraction changes. And I would say that that would drive some theorizing where you would now have to think, right, I have to account for that. So I now need a model of self-regulation or adaptation or something rather than just observing a difference at different points. One place could be in the categorization process. Another very natural place could be at the representational process. You could imagine hierarchically building a model of representational change that gives some account for how you might move from one to the other. I said I was going to say something about the similarity and rules debate. So here are the experiments where in some cases people were encouraged to use rules, and if you look at the structure of the rules, it really asks them to bring these guys together and bring these guys together, depending upon exactly which one of two rules they were trained to use. And you can see in this rule-based one, it's making the inferences that people are combining things along here versus things down here. You can almost see the nature of the rule that they were trained on in this case. But when they're asked to do it freeformly, they're not trained on the rule that leads to the correct categorization performance. They maintain an exemplar type representation and basically learn it by rote. And the important point is that you can pick this up in the gamma parameter as promised. So for the free categorization, it basically stays at its prior because it's not doing any merging, and then you've got no evidence about whether similarity is important. But when it's doing this sort of merging, which isn't similarity based at all because it's being driven by these rules, it detects this very quickly and says similarity isn't important in the abstraction that's going on here.
So does that allow function to be more systematic or less systematic?
Function?
I mean, because I was looking at some of Bayesian, I'm just trying to get to this Bayesian theory, and I know that they use it in
Yeah, so I'm familiar with both of those bits, and I'm really struggling to bring them together.
always.
Yeah, okay. I think this is my last substantive slide. So here are 4 other bits and pieces that came up. This is looking at 2 different subjects on exactly the same task. So here's somebody who doesn't abstract very much, and here's somebody who forms 2 very big prototypes to do this task and make some errors by doing it. But you know, those errors are entirely consistent with doing this sort of abstraction in their representations. So this strongly suggests that there can be individual differences in category representations, which shouldn't come as any surprise. I don't have a slide. I should have put a slide in. This would be super easy to model, and in fact there's a lot of work along these lines by adding yet another level to the hierarchy that says individual differences, so that instead of everybody getting exactly one level of abstraction, every individual samples their abstraction from some possible population, and this could be a mixture, or this could be all sorts of things. And that we've had a lot of success with that sort of individual differences modeling in this hierarchical Bayesian framework. That would be a nice thing to do. Another nice thing, and you know your model served you well when it sort of shows you how it was wrong and suggests ways for future development, you know, that sense in which modeling is not to provide answers but to sharpen questions, Here's a data set where it looks very much as if people are doing merging where they can with similar stimuli, but this one's an outlier, so a sort of prototype plus outlier type representation, which currently isn't built into the semantics of the way we generate things, but you could imagine having something other than that merging process that did capture that very directly. At least we're able to represent this because we have the notion that these three things could be merged, but this one's maintained as an exemplar, so we can represent it even though the theta and gamma parameters don't correspond exactly to it. Here's one where not only do the theta and gamma not correspond to what we want them to mean, but we can't even really represent it. So this one looked very strange initially. I don't know whether anybody can figure it out on the fly because this took us weeks, but then you guys are a lot smarter than we are. Here's the sort of merging that was inferred for one of these crisscross category structures. This one's maybe the cleanest one to look at, where this and this were merged with each other and this were merged with each other, which seems a very strange thing to do, but it has a really natural interpretation, because if you look at the results, that basically amounts, just because of the happenstance of the geometry of the thing, to preserving these two middle ones and deleting the two on the outside. So the net effect of all of this merging is basically to say, ignore that stimulus and ignore that one, I only need these two middle ones to make my decision, which is right for this sort of category structure. So it suggests one way in which that representational class that we started with of all the mergings is hopelessly misspecified and needs to be augmented with some notion of you can delete things rather than just merging them. So the modelling has shown you how wrong it is, but has done it in an informative way where it's pointed you towards what the right thing to do is next, and we like that. Okay, so what I hoped to do was show one concrete example of a hierarchical Bayesian attack on a problem in category learning, and you can see I've cut and pasted this because it's still covert here. Tried to show how you could take a model selection problem of choosing between this large class of 15 different representational models and convert it into an easier and more informative problem of just estimating the level of abstraction and similarity emphasis in forming them. Give one approach to developing theoretically satisfying priors and showing how that could come from a hierarchical notion. One that gives additional information and especially useful for making things commensurate across multiple tasks and experiments. And I think this is the really important one. Forces theorizing to go to deeper levels of abstraction, because you now have to think about where the things that were previously the abstract things, where they came from. And this is the basis for tying things together, I think. Thanks very much.
So I guess the modeling dimension of prototype exemplar controllers is things like something that
Yeah.
have you looked at any of those data?
I believe Wolf has. I don't know the answers.
What's Smith and Newton?
So they have an argument that, I mean, so I think the sort of general consensus is that exemplar models probably work better than prototype models for mechanical role in terms of results. And they've made the argument that if you look early in learning, you actually see something that looks a lot more like a prototype model that in fact across other tasks you can sort of find them, and part of it is just the power of the exemplar models to account for the data that makes it look like those are the better models. So it's a case where they think that they've got definitive data that supports people using prototypes. So it'd be interesting to know.
I agree. Yeah. Yeah.
When you have two populations trying to categorize one alien A and alien B, and they have two different concepts of how to categorize, but there's one right concept. Do you have any recommendations on what you think would be the best way for them to come to a consensus on how to categorize?
It depends a little bit what you mean by right concept. So one way you can think about right concept is, I know how I generated these and I want you to uncover the thing that I used to generate them. I think I have a lot of problems with that. That's a sort of common conception in simulation studies and all sorts of other things. But I think I have a lot of problems with that because there are many inferences that can be justified from sort of finite data coming from some true generating mechanism. In fact, the correct inference is the one that's justified by the data, not the one that necessarily corresponds to the sort of putative truth in the generator. So I would sort of want to unask the question. I think I would ask a question about which of these two groups has the inference that's best justified by the data, and that would be the one.
But the problem is that your prior has to enter into the decision about which inference is best justified by the data, and then you have to justify your prior, right?
Right. Which is asking the same question at a deeper level of abstraction.
Yeah.
And so it's a challenge in practice to convert many sorts of knowledge we have in psychological modelling into information that's suitably formalisable to enter into the calculations. But this was meant to be, in part, an example of one place in which, if you're willing to make some assumptions about how these things got generated, that is to do some psychological theorising, that automatically gives you a prior for other questions that you're interested in. Great, thanks guys.